Perfect. I see.
This works?
Yeah. So our next speaker will be Gideon Orelowitz, who will talk to us about the Kostka semigroup and its Hilbert basis.
Thank you. And yeah, thank you to the organizers for setting up this whole event and for allowing me to speak here today. So this is joint work with Gillian Gale, Joshua Kears, and Alex Young. And so this talk, the first half is going to be mostly setting up and explaining the main result, and then the second half will mostly focus on some interesting methods used in the proof of the result. If we're going to talk about the Kostka semigroup, we need to start at the beginning, and here the beginning is partitions. Simply put, a partition is just any finite sequence of non-negative integers that is weakly decreasing. We can represent a partition by its diagram, where the ith row of the diagram, we use lambda I, the ith part, left aligned boxes. So 3, 3, 1 is represented by 3 boxes, then 3 boxes, then 1 box. And we can also take the conjugate of a partition by just reflecting it over the northwest southeast axis. So for example, 3, 3, 1, when you flip it, becomes 3, 2, 2. And there's many different problems in math arising from just different ways to fill partitions with numbers. The one that is relevant for today's talk is the semi-standard tableau. So to a semi-standard tableau of shape lambda and content mu, you start with a diagram corresponding to lambda, and then you fill it with mu1's, mu2's, and so on, such that it is weakly increasing from left to right and strictly increasing from top to bottom. So for example, if we have shape 4, 2, 1, you see 4 boxes in the first row, 2 boxes in the second row, 1 box in the third row. And with the content being 3 1's, 2 2's, a 3, and a 4, there's exactly 4 ways to do that. And so we say the Kostka coefficient of 4, 2, 1, 3, 2, 1, 1 is 4. So these Kostka coefficients show up in quite a few areas of math. So where they come from, that I'm most interested in is in the transition between various bases of the symmetric functions. So for example, from the monomial basis to the Schur basis, and from the Schur basis to the homogeneous basis. They also show up in representation theory as the dimensions of the weight space of the irreducible representations of the general linear group. And they also show up in the study of Schubert varieties. And among all of these different places where they show up, sometimes it's not necessarily, the question isn't what's the exact value of the Kostka coefficient, but instead just is it 0 or non-zero? And if indeed the Kostka coefficient is non-zero, we say that lambda dominates mu, and we write it like this. And this notation is very indicative of a partial ordering, and that's not an accident. It turns out that this so-called dominance order is a partial ordering and is exactly well understood. Lambda dominates mu if and only if the 2 partitions are the same size, which makes sense because you need to have the same number of boxes as labels to have a semi-standard tableau. And you also need the kth partial sum of lambda to be greater than or equal to the kth partial sum of mu for all values of k. So for example, 6, 2, 1 dominates 3, 3, 3. You can check that for yourself. But 6, 2, 1, and 5, 4, 0 are incomparable because 6 is greater than 5, but 6 plus 2 is less than 5 plus 4. So the partial sums aren't aligned. Similarly, 4, 2, 1, 0 dominates 3, 2, 1, 1. That was the example a few slides ago. But 4, 2, 1, and 3, 2, 0 are incomparable because while all the partial sums of the first one are more than the partial sums in the second one, there aren't the same number of boxes as labels, so they are incomparable. There's a number of interesting properties that this dominance order has. One of them being that if lambda dominates mu, then mu conjugate dominates lambda conjugate. And more relevant even more relevantly for this talk, is that if you have two pairs of partitions such that the first one dominates the second one, then the sum of the first partitions dominates the sum of the second two partitions, which is to say that this has the so-called semigroup property. So a semigroup is just is like a group, except you don't have to have an inverse element. You just need to have an identity element and be closed under the addition property. And it turns out that this, the property I just described, means that if you look at the set of pairs of partitions such that lambda dominates mu, that forms a semigroup. And furthermore, this Kostka semigroup is a pointed cone. The definition of that isn't important for this talk. What is important is that this implies that it has what is known as a Hilbert basis, which means a minimal generating set of irreducible elements. So there's a finite collection of elements such that none of them can be expressed as sums of smaller elements, but they generate the whole cone. And so if we could understand this Hilbert basis, and we knew exactly what elements were in the Hilbert basis, this would be very useful to understanding the Kostka cone, because in particular, if you could show there was a property that was true for every element of the Hilbert basis and that was preserved under addition, then you would have shown that it's true for every element. And just for reference, this is the Hilbert basis for R equals 4, so pairs of partitions with at most 4 rows. And yeah, so it's clear just from looking at this that there isn't like an obvious pattern that calls out to people. And to go further into the answer, we're going to need to take a brief detour into complexity theory. So a decision problem is just any problem where the answer is true or false, such as here's a number, is it composite? And then we say that this problem is in NP if you can verify the solution given some amount of evidence in polynomial time. So for example, is this number composite is in NP because while it might take a long time to determine it, like from first principles, if somebody just gave you the factors, you could convince yourself very quickly that yes, this number is indeed composite. And the hardest problems in NP are called NP complete. And by hardest problem, we mean that if you can solve an NP complete problem in polynomial time, you would be able to prove every problem. You would be able to solve any NP problem in polynomial time. So yeah, so another example of an NP complete problem is subset sum. You're given a set of positive integers and you're given a target number and you're asked if there's any subset of that set that sums to your target number. This is, you can see again, this is an NP because this might take a lot of brute force, but if you're just given the subset, you can convince yourself that the answer is true very quickly. So why are we bringing up all this complexity theory stuff? Well, it turns out that the question of is this element in the Hilbert basis or not is an NP complete problem. We know that it's in NP because if you were just given a decomposition, you could convince yourself very quickly that indeed this isn't in the Hilbert basis. And we're able to show that it was NP complete by showing that a polynomial time solution for this would also be a polynomial time solution for the subset sum problem. So this is at least as hard as the hardest problem in NP. So this also has to be the hardest problem in NP. So this means that if we were able to come up with a classification for the Hilbert basis of the Kostka cone, we would have in short proved that P is equal to NP, which if we were able to show that were true, we would get $1 million and get our names in every computer science textbook. And so assuming that we're not the best computer scientists that have ever lived, we're going to assume that we're not going to solve that problem and instead narrow the scope to, is there any necessary condition that we can give on this Hilbert basis? And for this smaller problem, we were able to show the width bound, which is to say that to be in the Hilbert basis of Kostka R, you need lambda 1 to be less than or equal to R. and lambda1 is only equal to R if and only if the two partitions are conjugate rectangles. So this is perhaps easier to see than it is to just read. So here's the Hilbert basis again. Here R is equal to 4. And you see that lambda1, which is the first row of the left partition in each pair, never has more than 4 boxes in it. The width of these partitions are bounded. And in fact, the only time where this bound is met, which is these last 2 pairs of partitions, these are conjugate rectangles. So we are able to show that this is true for all values of R. So, and thus show that these Hilbert bases don't get arbitrarily large. So yeah, so this Hilbert basis problem, what's the Hilbert basis of a cone, is a very geometric problem, trying to describe a geometric object. And the initial inspiration for this problem came from studying the Kostka coefficients in the context of symmetric functions. So we have a geometric problem that comes from this algebraic combinatorics thing. So of course the proof is going to require graph theory, and in particular the Gale Riser theorem. So for people who might have forgotten, the Gale Riser theorem is classically taught as a necessary and sufficient condition for when a bipartite graph has a perfect matching. However, there's an alternate reformulation of it that gives necessary and sufficient conditions for lambda dominating mu. In particular, it says that lambda dominates mu if and only if you have a 0-1 matrix such that the row sums are mu and the column sums are lambda conjugate. So for example, here we have a 0-1 matrix where the rows are 3, 3, and 3. And the column sums are 3, 2, 1, 1, 1, 1, which is just 6 to 1 conjugate. And therefore 6 to 1 dominates 3, 3, 3. So Gale and Riser were able to prove that. And furthermore, Riser gave an algorithm that produces a canonical one of these 0-1 matrices for a given pair lambda mu that's in the Kostka cone. So we have this canonical matrix for every element of the Kostka cone, and we're going to do several seemingly random operations to it. First, we're going to generate a new matrix by subtracting from each row the row below it. And so originally we had a 0-1 matrix, and now we're going to have a 0-1, -1 matrix. Then we're going to draw a vertical edge from each of the ones to any negative ones in the same column. And we're going to draw a left pointing edge from each negative one to the next one in the same row. So we've taken this 0-1 matrix and turned it into a directed graph, and in fact, a directed forest. So here's a couple examples. In the first case, when we subtract from each row the row below it, we just get 3 vertices, and since there are no -1s in this, this graph is just going to be 3 isolated vertices. For this one, if we subtract from each row the row below it and then do the same operation, we get that there's 3 components, each of which are directed paths. And then if we do this in the last one, we see that this is a directed tree. So we call these KGR graphs, or Kostka Gale Riser graphs. And it turns out that these are always going to be directed forests. So we have these, so we've taken this pair and we've turned it into a graph. Why? Well, in this graph, we're going to look for a specific subgraph called a conservative subtree. And a conservative subtree means one of 2 things. It either just means any non-trivial connected component. So for example, here we see that in red, we have a conservative subtree, or it's something a little bit more complicated. You look for a subtree such that there's a -1 is your unique sink. One of your sources is a 1 in the same row, and every other source is also a source of the larger graph. So -1 is our unique sink. This one is a source in the same row, and this one is a source that was a source of the original graph. So we have this artificial seeming KGR graph. We have this, and in there we're looking for this very artificial thing called a conservative subtree. Why? Well, what we were able to show is that if the KGR graph has a conservative subtree, then you're forced to not be in the Hilbert basis. And the general overview for why this is true is essentially you look at the columns that have vertices in the conservative subtree. So actually in both of these examples, columns 2 and 3. And if you break up the original Riser matrix into columns 2 and 3 and all of the other columns, those create 2 smaller Riser matrices that corresponds to a decomposition of your original lambda and mu. So having a conservative subtree means that you're not in the Hilbert basis. And we're able to show that lambda1 is greater than r, which just in the language of this these KGR graphs just means that you're wider than you are tall. Then you're forced to have a conservative subtree by the pigeonhole principle, and a bit more of an argument, actually. So these two things together give us the width bound that we were looking for. So in conclusion, the Kostka coefficients show up in a lot of places. And we would like to be able to talk about the Hilbert basis, because that would give us an easy way of understanding the cone, but that's NP complete problem, so we're not going to do that. But we were able to come up with a necessary condition by using these KGR graphs and coming up with these conservative subtrees, and which seem to work. So in the future, we're hoping to use these KGR graphs and these conservative subtrees to come up with perhaps stricter necessary conditions for this Hilbert basis. And hopefully we could use a similar type of process of converting elements of a cone into a directed graph and looking for subgraphs in it. We could use that to describe other cones that maybe have similar matrix representations. We tried in particular for the Littlewood-Richardson cone, but we've had difficulty with that. So yeah, thank you. Anyone have any questions?
Let's thank the speaker. Are there any questions? Just a second, because there's a lot of clapping hands, so I have to see if there's a raised hand. I don't know. Well, there's one in the chat. Somebody asked, did you mean not Kostka Hilbert is NP complete?
Thank you. Yeah, that's a yeah, I misspoke. Yeah, so that's a good point. So specifically, NP to be an NP, you need some sort of witness that prove some bit of evidence that would prove that the answer is yes. And here, if you're given the decomposition, that's a proof that would be evidence that the answer is no. So the question, is this pair not in the Hilbert basis, is an NP complete problem? So yeah, that's a good point. Sorry for misspeaking.
Are there any other questions? Let's thank the speaker again.